When you pump gas into your car, it is easy to picture a direct pipeline to the prehistoric past, a liquid extract of ancient plants and organic matter pulled straight from the earth. We consume nearly 27 million barrels of this specific fuel globally every single day. This simulation of raw crude oil reveals a thick, chaotic soup of carbon and hydrogen chains moving sluggishly. Pouring this raw sludge directly into a modern internal combustion engine would destroy the cylinders. The heavy molecules refuse to burn cleanly, while impurities like sulfur and sand immediately foul the moving parts. The clear liquid dispensing at the station is a highly synthetic, precision-engineered explosive. It requires ripping ancient organic matter down to its atomic studs and rebuilding it from scratch. Before any chemistry happens, a refinery must physically wash the incoming crude oil. This diagram illustrates fractional distillation. Superheated crude is pumped into a massive column. As vapor rises, the temperature drops, separating hydrocarbons by boiling point. Looking closer at the upper section, engineers isolate chains containing exactly 4 to 12 carbon atoms, the precise molecular weight for gasoline. Simple boiling only yields a tiny fraction of usable gasoline per barrel. This leaves engineers with a massive volume of heavy, useless oil and a global demand they cannot meet through physical separation alone. To solve this volume shortage, refineries use a violent conversion process called fluid catalytic cracking. In this process, intense heat and pressure work with a powdered catalyst to physically snap heavy, long-chain hydrocarbons into shorter, highly valuable gasoline molecules. This schematic maps the anatomy required for that destruction. Notice the central reactor and catalyst riser, where vaporized feed forcefully mixes with hot catalyst. Following the flow downward, the regenerator burns off carbon deposits at 715 degrees Celsius, providing extreme heat to keep cracking oil. By forcing heavy oil to break into lighter molecules, refineries override the natural composition of crude oil. They chemically synthesize the exact volumes of gasoline the market demands. Cracking provides the right size of molecules, but they are often the wrong shape. Straight-chain molecules ignite too quickly under pressure, causing damaging explosions inside an engine known as knock. Through reforming and isomerization, engineers physically bend these straight alkanes. Watch as the straight chain twists into a branched isomer, and another folds into a circular aromatic ring. This complex geometry is exactly what an octane rating measures, representing the fuel's ability to resist premature explosion. The final product is a specific blending cocktail. Refiners mix the reshaped gasoline with oxygenates like ethanol for cleaner burning, alongside proprietary detergents and stabilizers to prevent engine resin. Refineries even alter the chemical recipe by season. In the summer, they lower the Reid vapor pressure by removing volatile compounds like butane, which prevents the fuel from evaporating in the heat and forming smog. The clear liquid at the pump is a bespoke, constantly shifting chemical cocktail, engineered to balance engine compression, emissions regulations, and seasonal weather. Looking at this view of a modern oil refinery, you can see the staggering scale of the operation. This molecular ballet happens continuously, 24 hours a day, inside massive, city-sized labyrinths of steel. Mastering this high-octane gasoline recipe directly enabled the performance of these military bombers, a chemical feat that directly contributed to winning World War II. Because gasoline is simply a specific arrangement of carbon and hydrogen atoms, engineers no longer require crude oil to make it. By breaking down plant biomass or algae, they can synthesize drop-in renewable gasoline that perfectly matches the C4 to C12 chemical profile. The next time you hold a heavy fuel nozzle, you are dispensing a highly synthesized, perfectly balanced chemical masterpiece, engineered over a century to power the modern world.